We've still got our red atom and our green atom falling down, but I've added in this floor below here. And basically when they reach the floor, they're not going to be allowed to go any farther. And so basically what we're doing, we've got the Euler chromer set up here like usual, but then we check for whether there's a collision with the floor. So right now there's no collision with the floor, and so everything is normal. But if at any point one of them is touching the floor, it's not allowed to move, or it's not allowed to move downward, I should say. And so basically the red one here is going to hit the floor with a downward momentum, and so it's not allowed to move down anymore. And so we're just going to set its momentum to 0 until it gets a positive momentum thanks to its green buddy up here pulling him back up. And so when that red atom hits the floor down at this point, the green atom ends up going down and then it pulls it back up thanks to the spring force. Let's watch that again. It's going to happen again when it bounces. So now there's a lot of vibrational energy in here. And so now, see, watch, the red one hits the floor and then the green one shoots back up. It extends the spring, which pulls the red one back up. And so you can use this as a model of a bouncing ball. This is exactly how a bouncing ball works. The only difference, and you should always be careful anytime a physicist says the only difference between two things. The only difference is here we've got two atoms and a bouncing ball has many, many Avogadro's numbers of atoms connected by many, many more springs than this. But this is essentially the way that this problem works. And what you notice is that the red ball, when it's in contact with the floor, it's stationary. So we're deforming. If you think of this as a bouncing ball, we're essentially deforming the bouncy ball at that point, because that's what happens, is that the bottom gets flattened out against the floor. And so during that deformation, we are losing some energy. And so what you see is it doesn't go back up as high as it normally does. And so we get a lower peak every time. And that's exactly what happens when you have a bouncing ball on the floor, is that it bounces back up, doesn't go quite as high, bounces back up, doesn't go quite as high. And so we're modeling that pretty well here. One of the things that I do think is interesting is at the end, you've got them still oscillating a little bit, but you've got a nice a pretty fixed distance between the two. So this is, the ball doesn't collapse on itself. You still have these springs going back and forth. And so the red ball kind of comes to equilibrium here. The green ball comes to equilibrium here. And so you've got this model of a solid, kind of resting on a surface. But what I thought we could do would be to add in the graphs of energy that we made a couple episodes ago. I've got those accessed right here. And so basically we need to add in all of the G curves first. Let's do copy. And let's see, we did that right under the grav here. Let's do paste. Very good. And then I need to add in all of the energy calculations. I've got that here. It's right underneath update spring. Let's see, update spring. Oh yeah, I need to delete that comment there. Go. Maybe paste. And then we need to add in the actual plotting down here. Copy, so immediately underneath what I just added. There we go. So now we'll have graphs. Again, these are graphs of the red ball's kinetic energy, the green ball's kinetic energy, the spring's potential energy, the gravitational potential energy, and the total energy. So let's see what happens with this. So the first part moves along kind of like what we've seen before. Red and green, their kinetic energies are increasing because they're speeding up as the thing falls. They're oscillating a little bit around each other because of that spring oscillation. The spring potential energy is actually not contributing too terribly much. I think that's because I pretty much have them at equilibrium, because they're pretty close to equilibrium near the beginning. The gravitational potential energy decreases pretty steadily, and then it's at this moment things start to go wonky. See, like right at this moment when they come into contact with the floor, the energies start to misbehave. So, for example, our total energy was constant here until we had contact with the floor, because none of these energies take into account an interaction with the floor. So as long as they're just falling through the air, this total energy will remain constant. But as soon as they come into contact with the floor, which they're about to do again, then we lose some energy. Where does that energy go? You tell me. That'll be one of your questions at the end of this video. But then we've got, so basically they're oscillating, they're behaving the way you would expect them to, like normal, until they come into contact with the floor. The floor is basically messing up our conservation of energy here. And there we go again, we lose a little bit more. That's interesting. So you lose some energy here, you lose another amount here, you lose a smaller amount here. That'd be interesting to try to figure out how much those losses are and see if you can model that. That would make a good problem at the end of the video, I think. But yeah, in between that, things are oscillating like you would expect. We actually get a little more oscillation of red and green in here. Actually, we get more oscillation in the spring here. Yeah, it's definitely oscillating more in terms of based on the distance here, and you can see that in the spring potential energy here. Actually, I just realized I have the center of mass on the same graph as the energy. Oops. So let's create a new graph here and put in paste there, and this will be time. This will be COMY. There we go. I realized I had two black curves on there, and I couldn't tell if I just couldn't tell the colors apart or if I had an extra graph on there. There we go. There's the COMY. Okay, so with that fixed, I thought this was a neat way to model a bouncing ball. I hope it's helpful to you as you are studying conservation of energy, and I hope you enjoy the problems at the end. Thank you so much for watching. I will see you next time, and as for now, I'm gonna bounce.